Okay, I think that we can start, please.
Very good. So good afternoon, good morning, good evening to everyone. My name is Alfio Quarteroni. I'm the MOX director, and I have the great pleasure and honor to host this evening for our MOX Colloquium, Professor Cherbel Farhat. Professor Farhat is the Vivian Church Hoff Professor of Aircraft Structures in Stanford. He's chairman of the Department of Aeronautics and Astronautics, and is the director of the Stanford KACST Center of Excellence for Aeronautics and Astronautics. Professor Farhat's research interests are mostly in computational engineering sciences, where he deals with the design and analysis of complex systems in aerospace, mechanical and naval engineering. Professor Farhat is a member of several academies, the National Academy of Engineering, the Royal Academy of Engineering in UK, and the Lebanese Academy of Sciences. He's a doctor honoris causa from the École Centrale de Nantes in France, and from École Normale Supérieure in Paris-Saclay. He's a highly cited author and a fellow of several prestigious associations and societies. Charbel has received many professional and academic distinction, and this includes the Ashley Award from the American Institute of Aeronautics and Astronautics, the Lifetime Achievement Award, and the Spirit of St. Louis Medal from the ASME, the Gordon Bell Prize, and the Sidney Fernbach Award from IEEE, the Gauss-Newton Medal from the International Association of Computational Mechanics, the Grand Prize from the Japan Society for Computational Engineering Science, and the very prestigious John von Neumann Medal from the US ACM. He was also knighted in France in the Order of Academic Palms, which is, I guess, the greatest honor in France for academicians. He is appointed on the Scientific Advisory Board of the US Air Force, and selected by the US Navy recruiters as a primary key influencer and flown by the Blue Angels. So Cherbel Farhat is an extraordinary innovator. He's one of the very few scientists worldwide who have really reshaped the field of computational engineering in the past decades. Charbel, thank you very much for having accepted our invitation to deliver a MOX Colloquium today on a very fascinating subject, computational mechanics for landing on Mars. Charbel, the floor is yours.
Thank you very much, Alfio. Thank you for this very generous introduction. For a while, I thought you were speaking about yourself, but so it is really a great honor for me to address this audience here. I'm going to talk about the inspiration for this title for landing on Mars is because, as you know, about less than 2 weeks ago, we in the US landed on Mars with Perseverance. And we have been working towards this project for several years now. And I want first to recognize here my people who have really made this possible. Phil Avery, who is still at Stanford, he's a research staff scientist. Jonathan Ho, who is still a graduate student, he'll be graduating soon. But everyone else has really graduated. And what is interesting here is where they have really gone. So Daniel Huang is at Caltech, so he's even closer to JPL. Ronald Borker is at ANSYS in the Discovery Life team. Sebastian Greenberg is at Amazon Web Services, and I'm still at Stanford. I also like to acknowledge several people that you see their name here at NASA, whether it's NASA Ames Research Center, and 3-4 people who really have been particularly helpful at NASA JPL, who have helped us do many of the verification and validation. And also Ben Tutt at Airborne. Airborne is one of the 2 companies that build the parachutes for landing on Mars, among other applications. Now, okay, how can I get rid of this? Okay. I don't know this yellow where it's coming from. So there has been 4 generations of NASA Mars rovers. The whole thing started with the Sojourner, which landed in 1997 as part of the Mars Pathfinder. Then we had a tandem of rovers, Spirit and Opportunity, who landed around 2004. That was part of the Mars exploration program. Then you can see Curiosity, that was part of the MSL program, the Mars Science Laboratory, which landed most recently, until recently, in 2012. And the 4th generation, which was Perseverance, that landed about 10 days ago. So the point of this slide is not really a commercial for Mini Cooper, but is to show you how the sizes of the rovers have evolved across the years. Already in 2012, the rover was about the size of a car, that was the Mini Cooper. Perseverance is about the same size, 126 kilos heavier, but it will grow. It's anticipated that the next one will be about the size of a minibus. So in order to understand how size really affect things, let me show you a little video that highlights a little bit what it takes to go to Mars. So it's a multi-stage rocket system. And then it takes about 8.5 months where you hope that everything goes well. And here we are at the last stage where the crew's separated and you have the capsule getting within 10 minutes of landing on Mars. You can tell from the video what you have to go through, the heat barriers, the slowdown. These are the thrusters now that are trying to guide the trajectory. And then at some point you have to slow down around, we are roughly around Mach 2.5. And at Mach 2.5, 2.2, depending on, you pull a parachute. You pull a parachute to slow you down. And only when you have slowed down sufficiently, you can eject the heat shield, and then you can eject the rover, and the rover takes out with thrusters, and then you land. So it takes the ride on the parachute is about 2 minutes. And then from the parachutes to landing, it's another 7 minutes. And this 7 minutes is about the same amount of time that you need to telecommunicate with JPL, with the control room, so that you can inform the room that everything, worked well or didn't work well. So those last 7 minutes are dubbed by NASA as the 7 minutes of terror, because for 7 minutes, you don't know what has happened. And what has happened has already cost $2.5 billion and 8.5 month journey to get to Mars. So the parachute has always been a great, component, a critical one. And it is the final ride of about 2 minutes that makes it happen or not happen. And until today, it's about 15 meters diameter. There are multiple ways to measure the diameter of a parachute because it has a parabolic shape when you open it. But this is a little bit the size of Curiosity. This is the one now that landed a few days ago, Perseverance. And you can see that it's roughly the same size. It's a little bit bigger, but not much bigger. The one DGB on Curiosity was already 35% larger than the previous one. This one is about the same, and you can see perhaps why. But the rover got heavier by about 14%, 126 kilograms. Now, all these things are flight tested. I don't believe that computational mechanics will ever replace flight testing, but I will highlight a little bit what's the role of computational mechanics in all this. So now what you see here is the opening of the parachute. So it's being pulled out by the balloon, and then you can see the unfurling. So this was part of the Aspire program in 2017 to qualify the final parachute that will be selected for Perseverance. And clearly they made the right choice. And here's the parachute opening. And look at the dynamics of the cables, because we will talk about them. So that was a successful test. There were 3 of them around 2017, 2018. But it hasn't always been like this. These are now tests for larger parachutes, 22 meters instead of 15 meters. This is for beyond Mars 2020. So this is the demonstrated technology for the next step. And you can see that that was very concerning. So these are flight tests. Both parachutes failed in 2014 and in 2015. Other tests also confirmed the failure. Now, what is really intriguing from a scientific viewpoint is that the one at the left failed at 9,000 pound force. The one on the right failed at 79,000 pound force. But on the ground, they were all tested with loads up to 121,000 pound force. So what was the difference? The difference is that in the wind tunnels on the ground, these were tested subsonically, but the dynamic pressure was taken high so that you can achieve these loads. But the flight test was supersonic because you open the parachute at a Mach number between 2 and 2.5. And that shows that in the failure mode, it's not only about the maximum load that the parachute takes, but it's also about the flow regime. And there is something about the supersonic flow regime that clearly is having a big effect here. There is also the fact that it's a much larger parachute. You can question whether we really understand the scaling laws for the design. Some people question the design itself because these were slightly different designs from the previous ones. But the point is that to go beyond 2020, we have to have parachutes of larger, even larger diameters, because the payloads will be even bigger than we have right now. Now, the program really goes back to the early 70s, and NASA had the Viking missions. And the point of this slide is to tell you that everybody seems to have understood that the critical thing is really the deployment of the parachute. The maximum stresses occurred during the opening of the parachute. No one had really a good understanding of what happens at the fluid structure interaction in supersonic flow. But yet, if you look at all the computational modeling that has been done, it has predominantly focused on analyzing the post-inflation regime. So you assume that everything inflated well, you get to the final shape of the parachute, and then the design focuses on making sure that the parachute generates the amount of drag that is needed in order to slow down the rover or the capsule that it contains it and land it. So the problem is that you need to get to that point, and everything I'm going to talk about is before you get to that point. So it's the deployment of the parachute, preferably out of the bag if we can do so, but at least from some crumbled position all the way to the final position, because this is where it fails every time that this has been seen to fail. So this is a terrific problem. It is very exciting, but it's incredibly challenging. You have to deal with shocks, with turbulent wakes, geometric and material porosities, all kinds of nonlinearities, massive self-contact. And more importantly, it turns out that the cables play a very strong role in this thing. And think about capturing the fluid structure interaction at the, at the level of the cables, which are 0.07 millimeter thin fabric. Some go all the way to 3.5 millimeter, and you have to insert them inside the CFD mesh and capture the FSI, or you have to do what some people do some body force modeling. We will discuss this, and eventually incorporate material failure. Now, another challenge that is here is this really raises the bar for graduate students. How do you involve graduate students in such a research effort, and you expect them to know about some intersection of all this material that you see here? So these are some of the challenges that we have to deal with. Now, let me start a little bit in an unconventional way and show you the simulation, the computational model that we have built. So clearly, when you see the large deformation and the opening of the inflation of the parachute, this tells you that we are talking about an embedded boundary method or an immersed boundary method for CFD and FSI. You can see that there is AMR around the shocks. We're trying to capture the shock move quite a bit. And we have a wake, we have to capture the wake. So there is an AMR for the wake too. And you can also see that we're capturing the FSI around the suspension lines, because you can see the wake from the capsule below that is traveling all the way on the suspension lines and interacting with the lower part of the parachute. What you don't see is that there is a multi-scale modeling of the woven fabric, because this is a parachute, this is made of fabric. So how do you model fabric? And what you don't see also is that it's a porous material. It affects greatly the boundary conditions for the flow. And therefore that required subgrid scale modeling of the treatment of the porous wall boundary conditions. So I would try to talk a little bit about some of these things. And starting with the embedded boundary methods. So embedded boundary methods, I mean, this is not something new. They have been popularized under many names actually, under immersed boundary method, but this tends to refer to a very specific way of doing embedded boundary methods, Cartesian methods, fictitious methods. I remember in the early days of the domain decomposition meetings, there were lots of approaches, that could fit that description. So you have an Eulerian grid, and then you embed a structure in it, and whatever the structure does, the grid in the simplest form of embedded boundary methods doesn't move. It's there. That's why it's Eulerian. It's more the structure that deforms. You don't have to worry about mesh deformation and about robustness, but you have to worry about a number of other things. These have been discussed recently at numerous meetings. We have developed our own embedded boundary method known as FIVER. FIVER stands for finite volume with exact Riemann solvers. So what is exact here about the Riemann solvers is not exact in the traditional sense, it's exact in the sense that it's an exact two material formulation, because you have interfaces between structures and a fluid. Or you could have, if you have a multi-material problem, you can have different fluid-fluid interfaces, like when you're doing, for example, air-water applications or things like that. So it's a finite volume method that works with different media, and it formulates the problem at the left and right as a Riemann problem locally, and it solves it. We spent quite a deal of time to be able to endow it with nonlinear stability properties like TVD. The biggest issue in these problems is because when you embed, you can see that you're not going to have a perfect representation of the grid along this is not a body fitted grid. So you're going to have a lot of smoothness issues on the interface, because the interface is going to be jagged. We got it to work with URANS, DES, LES, with near wall modeling. The beautiful thing about embedded boundary methods is that they handle, they don't care whether you go through massive self-contact, material failure, if you do them right. The biggest challenge is to get AMR to work in the context of an embedding mesh, because in that case, since you are not body fitted, there is no concept of isotropy or anisotropy. You have to come up with a new concept for these things. And the AMR I'm talking about here, it's a multi-objective AMR that has different criteria for adaptation, that it has to track wall boundaries, it has to track boundary layers, it has to track shocks, it has to track distances between cables, it has to track a certain number of things. So that's what makes it really a technology. Now, they have a background mesh, and it could be anything. This is a mesh that you generate, in MATLAB in 4 lines. And then you immerse in it a structure. And of course, there is the issue of the boundary layer. So you can automate this simply by adaptive mesh refinement. So the whole mesh generation process is replaced really by an AMR process, but you still need a representation of the surface of the object. So you still have a surface mesh, but you don't have a volume mesh per se. Now, one of the things that I will also talk about is when you do this, if you have something like a thin cable that you see here for the parachute, so there is the chute, and then you have the suspension lines. How do you get an embedded boundary method to really understand that something that is subgrid scale with respect to the CFD embedding grid is there? And the other thing is that we had to develop a homogenized flux body treatment to be able to account for the porous wall boundary conditions. And it is something that has been verified and validated with data. So we are pleased with this. And it's really, we got most of the heuristic out of it. It doesn't require prescribing a mass flux rate, doesn't require any heuristic discharge coefficient. And most importantly, it's valid in all the flow regimes. Now, embedded boundary methods have these advantages. So you have to trade all the ease and facilities by the fact that what happens to the structure is not a major concern, but the fact that you have always to separate between active nodes and inactive nodes. Some people call them ghost nodes and real nodes. So you have here the nodes that are in red that are inside, let's say, the body where the flow is not happening. In the case of a parachute, it's such a thin surface that you simply have to realize that there is something between the green points and the red points, which is a boundary, and then you have to treat it. It's a slightly different issue, but they're all related. So you have to separate between these things, but this is just a reminder for everybody that the grid does not see the boundary. The grid sees the intersection of its own edges with the boundary, and therefore you have to infer the proper treatment of all these edges that intersect the surface. You have to do the treatment that will infer what would be the correct wall boundary conditions had you had a body fitted grid to impose. Now, this has not always been a very successful thing. As a matter of fact, but for us, there was no other choice. It is impossible to remesh. It is impossible to deform the mesh. So we had to go with an embedded boundary method. And we knew that for viscous application, it had a bad reputation. These are results that come from papers at NASA and at CTR, the Center of Turbulence Research at Stanford. And this is about the sensitivity of embedded boundary methods with respect to the relative position of the structure and the fluid. So on the left, you see an academic case where the structure is perfectly aligned with the grid. On the right, you see the case where it is not aligned with the grid. And this sensitivity to the alignment, along with other issues, ill conditioning that comes from the points that you can't tell if they are really inside or outside, has created a number of nonlinear instabilities like spurious oscillations, roughness of the solution, and let me show that, and lower order of accuracy in all cases. So this is the case where you see on the left the perfectly aligned case. This is a simple flat plate viscous calculation to get the screen friction coefficient. You can see that when things are aligned very well, you have very smooth answers and you have the right answer. And when you go to the left, sorry, when you go to the right, you get really not so good answers. And what even makes it worse is the fact that if you refine the mesh and you are not properly aligned, so mesh M2 is finer than mesh M1, the oscillations even, increase. So these have been very well documented. These are, the community that focuses on this has always used them to against, of course, there are those who really worked on that issue too, but I mean, a number of people, including commercial flow solver vendors, shun away from immersed boundary methods for viscous application because of that. And I want to explain what really is the reason. The reason is really the fact that we're talking about discretization methods where typically we put a high emphasis on continuity. But what we have here is in the method itself, any embedded boundary method you're going to build, unless you pay real attention, you're going to generate discrete events. So let me try to graphically explain these discrete events very simply. So you have here an embedding grid, a background grid, and then you have a structure that you see in blue, and it's separating, the intersection is separating the green points that are active from the red points that are inactive. And along each edge, you can see the easy edges. So these are the active, but then you have also the edges that are active-inactive, and these are the edges that cross the embedded surface. And then if you look here at the picture, look at the red nodes and look at the edges that are active-inactive. When the structure moves, well, some of the nodes are going to be uncovered and some new nodes are going to be covered. You have now a different set of active-inactive. So you have this in a one-time step, you have things that have moved from one state to another state. And considering that what you do in the active region is an approximation that is different from the one that you do in the inactive region, when you cross the states and you have, edge status changes, you are going to get an overall approximation process that is not continuous with respect to evolutions of the embedded surface. So this is an example here. So in Fiverr, if you are on the active edges, we simply use a Riemann solver, a standard Riemann solver, meaning an approximate Riemann solver. But if we are on an active-inactive edge, we first solve a Riemann problem along the edge that intersects the structure. And this is a Riemann problem that is fluid structure Riemann problem. That's not a fluid Riemann problem. We get the Riemann solution at the interface, and then we evaluate the flux, for example, the row flux, the HLLE, HLLC, using the reconstructed value that comes from the Riemann fluid structure interface. And this allows us to enforce the proper boundary condition because we infer it from the solution of the Riemann problem. So you have two different fluxes here. And of course, when you cross the line and you do a continuity analysis, the minute you have a discrete event, you're switching from one way to compute a flux to another way to compute a flux. So you have just thrown in a discontinuity in the approximation process, and therefore you're going to pay for it somewhere. You add to this the jagged interface, you add to this that there are extrapolations all over. The extrapolations are inversely proportional to the distance to the surface. So when you get close to the surface, you start having overshoots. So all these things complicate life at the fluid structure interface. Same thing with the diffusive fluxes. So I'm going to simply highlight a three-element approach to fixing the problem. So first, we have introduced the concept of a hybrid node. So instead of simply thinking of active and inactive, so we create another category of nodes that is somewhere in between, that is neither active nor inactive, but these are the nodes that are about to become inactive. So they are shown in blue. We call them the hybrid nodes. And their definition is that they are part of at least one edge that is an active edge. But as a result, they can also be part of a hybrid edge, or a hybrid inactive edge, or a hybrid active edge. So these are the blue points that you see here on the picture. And the idea is to simply say, then we introduce a hybrid node indicator function. And the idea is that not to switch immediately from inactive to active or active to inactive, but to switch there with some approximation function, some map that is continuous, and take us from the inactive stage to the hybrid stage to the active stage, and vice versa, so that we don't see this jump that you go from 0 to 1, but you go, continuously along this indicator function kappa that takes you from inactive to hybrid to active. So how does this change? Again, I'm going to explain it in the case of Fiverr. So in one case, we have to solve a Riemann problem between two fluid states. In another case, we have to solve an exact Riemann problem between a fluid state and the structure, what's happening at the interface with the structure. So instead of doing this, well, we have a universal approach now where we compute the flux between Wi and a convex approximation of something that could be either in the fluid or could be in the structure. So we solve the Riemann problem as we do, but we smooth it with these kappa functions and 1 minus kappa. And we do the same thing for the diffusive ones. And we have now a universal approach, meaning that we don't distinguish anymore whether you are real or ghost. It's always the same approach as what you see with these kappa functions. And that gives you can prove, of course, but I'm not going to do it here, that you get a continuous approximation process with respect to evolutions of the immersed boundary. So this is what we used to get. You can see here the jaggedness, and these were documented in these papers. And now with the universal approach, you can see that you get the same smoothness that you get on a body fitted grid. So that was one example of what we do. So let me move now to the supersonic porous wall boundary conditions. Now, there is something that is interesting. The most popular approach for treating porous medium in this community has been the Ergun equation, which is an empirical equation that relates the pressure to the velocity. I mean, there is nothing wrong with empirical. The whole engineering is built on an empirical relationship. It's a great thing. The only thing is that it really assumes that you are at very low speed because it neglects compressibility effects, and therefore it's really a subsonic approach. And there have been reasons not to be too happy with it in the supersonic regime. So Fiverr really gave us an opportunity to say, okay, since now we can handle Riemann problems between fluid and fluid structure, then if I look at the porous medium as being something, a medium that is characterized by a porosity ratio alpha, then I would say that when I have an edge that traverses the interface, an edge ij that traverses the membrane that is porous, well, it could go through the hole or it could be blocked by the structure. So why don't we say that we're going to do a convex mathematical approximation? We're going to say we're going to take alpha times a rho flux between air and air, and we take 1 minus alpha of a rho flux or any other numerical flux you want between air and structure. So we treat it as if it was really a linear combination of air, and air structure, and we do the same thing for the diffusive fluxes. And alpha can be either deterministic, that is given by the porosity ratio, or we have even toyed with statistical model to be able to get these alpha. And things worked not too bad, but there was one issue that came up when we do the validation. So this is where you compare to real data, that we understood that what this approach is missing is that when the flow goes through the pores, we are losing the friction of the flow around the boundary of the pore. I don't have a very good image here but imagine some circles into this infinitesimal element that you see in blue of the porous material, and then you have the flow going through it. This convex approximation that I showed you does it best to represent the treatment of the boundary condition, but there is still a friction of the flow around the boundary of the pores. So for this, we have developed a homogenization approach where we start from the compressible Navier-Stokes equation, and all what we care about is what's happening inside the porous wall. It's standard Navier-Stokes outside the porous wall, but inside the porous wall, we have average Navier-Stokes equation. And when you do the averaging, you get these terms that are shown here with brackets, and then they vanish around away from the pore because we have a periodicity assumption here of the solution, and these are derivatives that with respect to the directions of the homogenization. So these ones, we want to model them inside the pore so that we can get the effect of the friction between the flow and the pores. So when you do the discretization, it all ends up with a kinematic issue. So what we need now, we can, if we knew what is the profile of the velocity inside the pore, then we can get anything we want. So this is the approach that we've chosen here. So we're going to postulate the concept of an equivalent pore, which means that if I take an infinitesimal element of the porous boundary, I'm going to assume that it can be represented by an equivalent single pore. That single pore could have any shape. I'm going to postulate a parabolic shape of the profile of the wall, and I will derive an analytical expression to form a body force, and I'm going to, and this body force will be what I was looking for to model really these equations. Will be really, the body force will be what will be modeling the source term that you see here. So we have postulated several shapes. I'm going to show them to you. There is a latency here with the connection. So you can postulate a circular shape, a square shape, a gap shape. So we have a library of them. And for each one of them, we have postulated using a Poisson flow type of approximation only for the kinematics, not, so we will represent the compressibility effect. We can get the analytical solution for the velocity field inside the pore, and then we can use it to build the source term. Since we don't know exactly where to put it, so we put the Gaussian approximation of the Dirac function to put it inside the pore. And as a result, we go now to do the validation. So NASA did the experiments. They took the same fabric material from the ripstop weave, and we have looked at pores that are, square, rectangular, gapped, circular, and here are the results. The experiments you see are these error bars that you see in blue. So they had a range because, it's hard to get reproducible experiments. So these are the error bars, and you can see that no matter which shape we postulate for the pore, the single equivalent pore for an infinitesimal element, we get the correct velocity as a function of the differential pressure on both sides of the parachute. So that was, again, something that we're happy with. So this is now pore resolved simulation to compare with respect. So this is more like a verification. The other one was a validation. On the left, you can see the homogenized model that look at the whole thing as a 1D through the pore. At the right is really the pore resolved simulation. So these are DNS that go really for the flow through the pores. And if I look at the simulation, you can see that actually that they correlate pretty well. Now, I'm realizing that we're going through time. I wanted to talk a little bit before I conclude here with some more simulations, show you what happened with this. So we have to deal with the fabric, and with the fabric, we're dealing with, something that is really heterogeneous. We're not sure that all the fibers are well aligned. The experimental data is very rare. So we decided to go with the multi-scale modeling. It's at the macroscopic scale, we have a membrane, but the membrane does not see the weave, does not see the fibers, does not see the contact between the layers of the weave. So we have a microscale model where you see you have a solid element representation of the weave, and we have a macro scale model that shows you the fabric, and we're using FEM square as one approach to do the scale bridging. Now, to make a long story short, so you have two steps in FEM square. You have, you go to each Gauss point in your finite element model at the macro scale level. You can generate this to many level, and then you localize it. So you take your deformation gradient to infer boundary conditions at the micro scale. You solve a finite element representation based problem at the lower scale. You homogenize to compute, the stresses that come from the boundaries in the form of tractions, and you feed them back to the Gauss points. And this way you don't have to use any constitutive law at the macro scale. This will be essentially your constitutive law. And so you have to essentially solve a unit cell problem. You have to do this for every Gauss point, so it is incredibly intensive. And at the end, all what you're doing a multi-scale approach to essentially furnish a mapping between the macro scale deformation gradient and the first Payola-Kirchhoff tensor. Now, we could apply this straightforward, but let me show you what's really the difficulty, is that you can check in the literature. This has been all developed for solid to solid, but here we are in a different situation where we have a membrane at the micro scale. So we have a plane stress condition. And then we have at the micro scale, we have a solid. So now we have to communicate between the two, but they don't really communicate well during the homogenization step, because you have a Payola-Kirchhoff, first Payola-Kirchhoff stress that is 3D on the right, and you have a plane strain stress on the left that is 2D and a half. So we had to fix these issues. So this is something that we have proposed. You have to go back to continuum mechanics and look for a good pair of conjugate quantities. So we use the polar decomposition, go through the stretch tensor, convert it to a biostress. It's a bunch of mechanics that essentially you do so that you can transform something that is 3D to something that satisfies the plane stress condition, and you can get the scales to work. Now, what I wanted to show you is this now, does it work? Yes, it works. But the simulation you see here, look at the inflation of the parachute, look at the cable dynamics on the bottom right. You can see the chaotic motions of the cable. Remember that we have to capture FSI there. But if I want to do this multi-scale, we have done 10 time steps with the multi-scale. And based on those 10 time steps, we have concluded that it takes, on 1,000 cores, it will take 48 years to be able to implement this. This is why it's almost impossible to do something like FEM square without some other approach. We have gone through mother order reduction, but let me give you the short version of the story. You could simplify all this and postulate a linear model that connects the plane stress and the deformation gradient. You can assume a quadratic model. And then we decided to go with a neural network. So the neural network, we formulated in a certain way that it's a correction over a linear approximation, so that the neural network focuses really on the increment and not on the basics. And then we built a loss function, and we have to train it on a coupon. So the same way that people do coupon testing in a materials lab, we do here the coupon testing for the neural network. So we generate a parameter space that is, in this case, the strain space. And then we simply take a single element. That's what you see at the left. We have a single element, but that single element is a multi-scale element. So we build a reduced order model there to even reduce the training of the cost. So this is a projection-based reduced order model. And then we built this loss function that essentially says that I need to build a neural network that will able to reproduce for me what this multi-scale computation, what's the map that is furnishing. So it is, here is the results. So if I look now of how the stress and the strain that I get between the macro scale and the micro scale, looked at the linear model, for example, will produce all these straight line curve that is linear, so it could not capture, the softening that you get because these are, fibrous materials. The quadratic couldn't get it either. But on the other hand, when you go with the neural network, because you have essentially a nonlinear manifold that you're approximating, it gets it very, very nicely. And most importantly, it is really doable, and as I'll show you. Now, finally, this is the last part, is what do we do here on the fluid structure interaction of the suspension line? Now, the suspension line, if you really want to see how important it is, this movie should be able to tell you. So these are the shocks that develops, and you can see that the shocks travel along the suspension line. They completely change the type of the flow. And then without them, it's impossible to get any results that matches the flight test data. The issue is that when you insert a cable inside an embedding grid, so this is a thick cable of 3 millimeters, then when you go inside, you may not even intersect the grid. So the way to see it is that we dress those cables. So we do an embedded boundary square, if you want. So the cable is the finite element representation, which is the straight line or the curved line if it's higher order. But then we build an embedded surface that corresponds to the real geometry of the cable. And this embedded surface is what you see here. So we dress it, we constrain its kinematics to follow the kinematics of the suspension line, and we compute all the loads on this true cable that has the resolution to intersect if you do proper adaptive mesh refinement. So it will intersect the CFD grid, it can capture the load, and it can transfer the load to the cable element that is used in the finite element structural model. So let me just show you how this was validated with the Curiosity flight data. So this is now a complete disc gap band parachute system. It has the capsule, it has the bridle, it has the riser, it has the suspension lines, and it has the canopy. And this is why you need to work with NASA to be able to access to all these data. This is the finite element model. It's a detailed finite element model. It's as realistic as it can be. It has almost everything, the suspension lines, the canopy, the geometric nonlinearities, etc. And you need now the initial condition. Well, it turned out to be pretty hard to really simulate getting this outside the bag. So we started from something that is a chute. So this is the geometry of the parachute. So first we simply pull it. So we stretch it. You put a unit load on the top of the parachute and you pull it. You pull it, pull it, pull it. And this is the crumbled state. You have massive self-contact here. And we assume that this is when it gets out of the bag. It is in this shape. And then we do now our CFD around this. We start from it. We have AMR. We specify, since this is all LES based, we specify the scales that we want to capture in the wake, near the body, in the capsules. So typically we end up with about 55 million nodes, and this is with AMR and with the suspension line. And this is a high resolution simulation that shows you the inflation. And you can see, again, the waves traveling on the suspension lines. It's kind of similar to the movies I showed you earlier. And this is now a view of the parachute from inside. I think it's a great painting. So this is the interior view of the parachute. And of course, the issue is this predictive? So at the left, you have the numerical simulation. At the right, you have the flight test. If you focus on the picture, you can see that we see really the wrinkling. It's qualitative. qualitatively doing not too bad, but most importantly, of course, are the quantitative results. So this is the inflation. You can see the star moving. So this is the result of the simulation. And you have the Curiosity rover data. So NASA has the data, and you can see that it's not too bad. It's predicting very well. So this is what NASA wanted to see before we can see if we can predict the failure. Now, this is all multi-scale. So you can see that we have all the neural network or the ReLU that are there. And actually, they gave the same results as the single scale, as the, without doing multi-scale, as far as the drag versus time. When we looked, however, at the stresses inside the parachute, well, the multi-scale version and the conventional modeling version don't give the same result, except during the early part of the inflation. And after that, there are significant differences, like 30%. We have an overestimation of the stress if we assume that it's a conventional material. And then we have much lower stresses. These are von Mises stresses if we assume that it's multi-scale. The unfortunate thing is that we don't have flight data for the stresses. We only have flight data for the drag. So we're working with NASA on ground experiments, if possible, to be able to validate these things and see what is needed. So this is my last thing. I wanted to leave it up for you with a challenge here. So we are doing now the validation for the Aspire program, the first that I showed you, and then we will be doing the validation for the Perseverance that landed a few weeks ago. And we already see that depending on the configuration, sometimes we don't get as good results as what I've showed you. And we believe it has to do with the initial condition. So how do we get the right initial condition? So we have to simulate, include now the parachute that is inside the bag and getting outside the bag. I mean, that's a pretty tough thing. So we have built one approach in 2D. This is, you can see here, the bag. You can see where my hand is. So this is folded, and we're going to unfurl it here. This is in 2D. And we were happy with that. So you can see that you can now inflate it. And it goes. And this was done. How was it done? It was done using space filling curves. So it's a mathematical approach that most of you know. So it's a mapping between 0, 1 and 0, 1 multidimensional, where we have done it only for d equal 2, and we have not been able to do it in 3D. So we need something like a space filling technique or something to represent a crumbled bag inside, a crumbled parachute inside the bag, and try to simulate its getting out so that we can get the right initial condition instead of this stretch thing that we have been assuming, because otherwise we are short of what could be causing discrepancies in some of the results we have seen. Thank you very much for your patience.
Thank you very much, Charbel, for this incredible and amazing numerical tour de force, where you basically touched all the forbidden numerical subjects, since there are many students in the big audience here. I have to say that when you touch all these chapters, you say, stay away from this aspect, from this nonlinearity, because it's virtually impossible to deal with it. And you show that actually you are a brave man, and eventually you had something that worked even in incredibly complicated and difficult and challenging conditions. So I have plenty of questions, but I'd like to leave the floor to the audience. Let me just start by asking one thing. When you say that you compare your artificial neural network for the multi-scale with the conventional single scale, what is the conventional single scale? Is an approach where you're actually resolving all the scales?
Okay, so that's a very good question. Unfortunately, because of time, I had to go quickly over it. So let me get to the right slide and tell you what I'm talking about. So what I call conventional modeling is Okay. It means that you have only what you see here on the left. You only have a membrane, and then you have a hyperelastic material. So you have geometric nonlinearity, but you have a conventional material model. The conventional material model, I mean, you can, assume any material model that you think is appropriate. Some people have developed tabulated material laws based on coupon test. So you have a sigma versus epsilon, relationship that is either given from data. People really underestimate the fact that people have moved to data-driven many, many years ago, depending on how complicated the material is. Or you can simply assume that it's one of your favorite constitutive laws. So that's what I mean, a conventional modeling. It's the map C that you see here between the strains and the stresses. What I call multi-scale modeling is you say, well, I don't really know what is the correct constitutive behavior here because it's too complicated. There are weaves, there is contact between these weaves, there are all these things. So you map them, you go across the scales. There is a mesoscale here that I have skipped. And then in this representation, we have a macro scale that is here, and then we have a micro scale that is here. So this is what I tried to say here is that at every Gauss points of the macro scale, we don't have the stress as a function of the strain. So what we do, we have the deformation gradient. From the deformation gradient, we go to the lowest scale where we have a geometry that could show you the feature. In this case, it was like, a hole. But in our case would be the weave with the contact between the different things. So it means that you go to the lowest scale where you can have a representative of what is really the true geometry when you go at the lowest possible scale. You solve there, it's easy to postulate a material law because if you are at the level of a fibril, you can do the test in the lab for a fibril and you can get the material law for that fibril. It's a simple, pull test. And then what you need now to work on is the upscaling. How do you go now from the information that you have here, a complete finite element model for which you have a material law. So you compute the tractions on the surface, that becomes the homogenization, and you pass the tractions all the way to here. And now it means that for every deformation gradient, I was able to return a stress. And therefore I have a map now between the strain and the stress. What the neural network does is that since you have to do this at every Gauss point for gazillion elements in your macro scale, at the end of the day, all this work that you have done here is for nothing more than to return a map, there is phi between the tractions on the boundary of the unit cell and the the boundary condition that you gave it. So you do all this work and you throw most of it out because all what you want at the end of the day are the tractions on the surface of the unit cell problem for a given deformation gradient. So you are computing a map phi between E and F. And all this work is just for this. I'm repeating myself. So the idea is that, okay, why don't you go and do this on a single element? You go on a single element that you see here. That's one element. And that's what people do really in their lab. You take one element and you go to the parameter space, and here you take as parameters all kind of strains that this element may see. So you have to calibrate carefully your range. So this is a plane, it anticipates that there's going to be a plane stress strain thing. So you have E11, E22, and E12. You vary, you sample if you want, just like what you do in parametric domain decomposition, parametric projection-based model order reduction, sorry. So you sample all these values here, and you say, what would have been, the sigma that I will have returned to the Gauss points. There is only a single Gauss point here for that element. And then you do the training this way. And therefore, instead of, when you go online, instead of doing this for every Gauss points by resolving the unit problem, you use the neural network that has already created for you a map between any possible strain that it may see and the stress that it will get. It's a perfect application for neural network. The biggest sensitivity is whether you train it with the proper range here of the parameter space. Is this any clearer?
Clear. Thank you. So just asking the participants to raise their hands if they have questions to ask. And so meanwhile, can you give us an idea of the typical time step that you have to use? And how does it fit with the space?
The time step?
Yes.
The time step is of the order of...
in the phase of deployment of the parachute, for instance.
10 to the minus 5 seconds.
All right. And I guess all your calculations...
I've shown you, including the multi-scale, take about 6 days on 3,000 cores.
And for how long do you have to simulate then? I mean, for how...
The inflation time is about half a millisecond.
Okay. All right. And another question: when you have shown this model for Navier-Stokes in the porous hole, say,
Yes.
if I understood correctly, you have then to fully resolve the fluid in the hole, within the holes, right?
Yes.
So you have this model that then should be coupled with the classical, say, compressible Navier-Stokes equations,
Yes,
upstream
absolutely.
and downstream.
Yes.
Okay. And how thick is the wall?
How thick is the wall?
Yes, the whole of the membrane. How thick is the membrane?
The membrane is of the order, I had it in the first slide, 0.07 millimeter. It's very thin.
Okay, so you solved the Navier-Stokes equation in such a tiny...
It's homogenized, remember?
Oh, yeah.
So,
sure.
Yeah.
Okay.
So all this is to compute a source term.
Yes.
But the source term is trained by the DNS resolved simulations, the poor resolved one. So here is the one that you see that it's really poor resolved. So, and this is only for a little piece of the fabric.
Yeah.
But what the real simulation see is this that you see here. So it's really 1D. And this is the correlation to show you that they give the same answer.
Amazing. I see there are a couple of people who raise their hands. Luca did them.
Yes, thank you, Alfio, and thank you, Professor Farhat, for this wonderful talk and very impressive. I have a question related to the initial condition. In particular, at some point you mentioned self-contact. Are you modeling it or?
Yes, absolutely.
Which approach do you use for modeling it?
We have both Lagrange multiplier and penalty.
So you use a combination of them or?
No, the most robust one is the penalty.
Okay.
But when we can, we prefer the Lagrange multiplier.
For computational reason efficiency or?
No, for accuracy.
Accuracy.
And the penalty method, I mean, the penalty method is coefficient sensitive. And then when you do a post-mortem verification, like in your simulation, occasionally you can still see that it did not do a good job at enforcing the contact conditions, which means that element could interpenetrate. So the Lagrange multiplier is more expensive. So that's what I said. If we can get away with it, we'll run with the Lagrange multiplier. So it all depends on the computational resources, on the time step and things like that. But we have both approaches.
Thank you very much.
Nicola? Rolini?
Thank you. Really, thank you for this really impressive talk. It was very, very interesting. I have a curiosity related to the temperature that the system reaches, and if it is a relevant feature also on the structural problem.
Yes, you're absolutely right. So so we have just finished our 4th year. So this, what I've shown you here is the result of 4 years of work. And we have now just received funding for 3 more years to continue working on this topic. And one of the issue is you are in the supersonic regime, and for the moment, we are not taking into account the fact that the material properties of the fabric are temperature dependent, and that because of the opening at such a high speed that may have a strain rate effect. So there could be a thermostructural, let me call it thermoelastic, but I mean, it's really a thermostructural, it doesn't have to be elastic, a thermostructural effect between, the heating of the system and the softening of the material and the behavior of the material. Now, this is on our plan. We have some initial results. The difficulty for me for all these is that, I mean, they are great, but if we don't have validation data, it is difficult when you have all these things to address. It is difficult, and I'm speaking here from an engineering viewpoint. I'm really not speaking necessarily from a scientific viewpoint. It's more from a practical engineering viewpoint. It's difficult to figure out what are the priorities. I mean, there are so many things. Is this more important than getting the right initial condition? Because there is some chaotic aspect about the problem. And let me tell you, we have done many validations. Overall, they all look good, but not at the same level, which means they miss details. But some of details are important if, for example, they underestimate the maximum stress. So the strain rate effect, the temperature effect, these are on the list of important parameters. For the moment, they are important because we don't know the answer. So we are suspicious. We say, oh, is that important? We don't have validation data. So now, this year, about a month ago, NASA announced the results of the new competition. So there are 3 teams working on this problem. There is us on the computational modeling, and the 2 other teams, they are charged with doing ground experiments to be able to answer these questions. I'm sorry for this long answer, but that's really what's happening. In the absence of validation data, it is difficult to prioritize things.
Thank you very much.
Yeah. So if there are no further questions, I'd like to I'd like to thank again Professor Farhat for this fantastic example of what you can dare to solve if you really have, well, of course, the knowledge and the vision. And of course, we'd like to congratulate you for this incredible success that you have had with NASA to assume the responsibility of such a great and important human endeavor. So thank you very much, Charbel, and thank you everybody for attending this talk, and goodbye.
Thank you very much, Alfio. It was really my pleasure, and I was very honored by the invitation. Thank you.
Thank you.